Okay, so hello everyone, welcome to today's reading group. So in this quarter, we are starting the course about diffusion models. So I think based on our current progress, especially the content covered by Zneo last Thursday, I think it's the right time for me to bring this paper, which can be seen as a combination of diffusion model with graphs to observe more about it. So the paper is titled GeoDiffusion, a geometric diffusion model for molecular conformation generation. So this paper is published in this year's iClear and has been selected as a oral presentation. So it's also from Professor Tang Jian's group. And the first author is Minghai Xu. So he has done a series of work on molecular graph conformation work, and later I will give you a brief introduction to such thread of work. So the key idea that I want to bring this paper is kind of want to give all of you an example that like the concrete idea of how we're going to combine this diffusion model with graphs. And actually, I also found there are many organized paper online from GitHub by applying diffusion model, for example, to time series data, to video images, NLP downstream tasks, etc. So I think if interested, you can also read them online by category. Okay, so let's get started. So let's start from the problem definition first, because it may not be very familiar to all of you about what is molecular graph conformation. So the motivation starts like this. In many real-world scenarios, we are required to understand the properties of moleculars, such as drug discovery, material discovery, etc. And traditionally, moleculars are represented in either 1D space, like a simple symbols comprised of several letters, as we learned in our chemistry class, or later on represented as 2D molecular graphs, where we have some nodes distinguished by their node type, and we know how they are bonded together with which type of bond. However, a more natural or intrinsic representation for molecular would be its 3D conformations, which basically represents each atoms in this 3D space by 3D coordinates, and also describes the potential edges with possibly edge features connecting them. So this can be used to determine its biologic and physical activities, such as charge distribution, interaction with other moleculars, etc. So compared to the 2D molecular graphs, it would reflect more geometric properties, such as the angles in the 3D space, and can be applied to more downstream tasks. So for real-world moleculars, directly computing its 3D structures from the 2D molecular graph is kind of expensive. So recently, people have started trying to see whether they can train a machine learning model that takes the input of a 2D molecular graph and then trying to directly generate its molecular conformation. So to be specific, they're trying to use this model to predict valid and stable conformations from molecular graph, where the model input is the 2D atom bond graph, and the output would be automatic 3D coordinates for each of the particles.
Notable, just curious, when we try to put the coordinates for each atom, how do we choose origin point?
Yeah, that's a very good question. So for this conformation, actually you can see if given such molecular graph, here I show an example of what would be the generated molecular conformation. However, it's not like like a fixed one, saying that, okay, if you just imagine that you just translate it by a direction or rotate it, it still will describe all the properties contained in this 2D molecular graph. So essentially, the data set itself is to giving pairs of such 2D graph to one of its or a set of its possible conformations. But within that set of conformations, each of them, for example, would represent not, for example, this one with rotation or translation, but that for this given 2D molecular graph, it can have distinguished like 3D architectures. So essentially, for each input 2D molecular graph, the underlying ground truth may be a set of such conformation. But the training example or test example is set as pairwise.
Now, I think my question is really, first of all, thank you for letting me know that there could be multiple 3D conformation related to the single 2D graph. My question, like for even for just one of them, one of those conformation, how we decide the origin point to make the coordinates unique?
Oh yeah, as I said, the coordinates, if we just shift this one or rotate it, it cannot be unique. And all of those rotation or translation make sense. So all they need to provide is just one kind of its 3D representation in a coordinate space.
Oh, I see. Yeah, I thought you said that there could be different topology, 3D topology corresponding to the same 2D topology.
Yeah, because the overall goal is just trying to generate the 3D coordinates which make sense to the 2D input. So you can just imagine when you train the model, even if for all of this data set, for example, for this graph, if you just change its label by shifting or rotate and then retrain the model, it will also, when you generate a new molecular 3D conformation, it will also make sense. Like in later on experiment part, I will show you some examples that they have generated.
They are saying that even for this, yeah, when I was thinking like general like translation or rotation for the entire structure, but I think Ray, you were talking about here also related to some local rotation, right?
I think maybe the more easy understanding would be that in order to make this conformation make sense, essentially it will need to, for example, preserve like for example, some pairwise distance between, for example, this particle and this particle, no matter how you change their coordinates, right? So like the structure or like the topology of the generated 3D conformation would describe all the necessary properties contained in the 2D graph input.
Yeah, but there are two levels of change. The first level is like to just make the 3D object do the translation and rotation as a whole.
Yeah.
Of course, in this case, right? So the coordinates, just follow the translation rotation. The second type of change is like we can maybe change the local structure. For example, for the point atoms that you have highlighted, right? So for that local one, you probably can rotate that. But that will make the local coordinates for those three atoms slightly different, but probably still corresponding to the same 2D graph on the left-hand side. But that kind of local rotation might cause different energy.
Yes.
Okay, so
I think what they mean may be the latter case, right? There's this local change. Just like if you think about people, right? So you take a picture, right? You have a certain pose, right? And then if you take a picture from a different angle, right? That's kind of a global rotation, right? And but if you take a picture of the same person, but you know, a different pose, then that's corresponding to this latter case. Like, you know, there's changes in terms of relative position.
Yes. So basically, I think the local change described by Yizhou is possible because originally some machine learning work, what they did is just following, I will introduce very soon, the two-stage procedure where they predict first the pairwise distance of all pairs of particles, and then they adopt a post-processing process to generate all items coordinates based on the predicted distance. And such procedure is not guaranteed to give you just one unique coordinates based on the predicted distance.
I understand. That's what I mean. Like actually in their paper, I think that they if I do not misunderstand their paper, they actually focus on the latter case, which is you know, allowing all these local changes, not just the global changes, rotations. That's what when people talk about molecular conformation.
I see. Okay, yeah, I think Fred has put something in the chat box. Yeah, I think like for the problem setting itself, I think it basically focus, if I understand correctly, is and also based on the generated molecular graph in their experiment setting. They're trying to preserve the kind of the if you can in the extreme case, it's just preserve the pairwise properties that it can learn from inferred from this 2D input graph, and then they try to based on such properties to get the 3D molecular conformation. So for the nodes, for example, that I highlighted there, in their illustration later on, we can have, but they will view it as not the same one conformation, but as other set of possible conformations corresponding to the same input 2D molecular graph. So for each input 2D molecular graph, they are able to have a set of corresponding molecular conformation here.
Yeah, so if two items, if they have a bond, right, the actual bond, like you highlight there, I think the relative distance, you know, it's about stable. But yes, for two items that do not connect by an actual bond, right, they're connected through, you know, other items, actually their relative distance can change quite a bit. In different conformation, that their relative distance can change quite a bit.
Yeah, but one thing in their implementation is that for this paper and also in other related work done by this author, for two particles that do not have a direct bond, they also incorporate a new edge type indicating that there's no edge connecting them. So essentially when they do the generation, you can just simply assume it has a fully connected graph when you train the model. But of course, for two nodes that are without any like real bound here, there's kind of no like direct distance that can be defined among them. As through the modeling procedure, they still consider such as a special type of edge.
So I think what we mentioned here and also our previous discussions try to say that for the 2D graph structure, actually information is less. So it has some ambiguity. For example, for the unconnected atom, right? On the right-hand side, if you rotate the local structure, then sometimes it has a bigger distance, sometimes it has small distance. That type of information is not able to be captured on the left-hand side.
Yeah.
Okay,
Oh.
so lots of ambiguity, right? So then that's related to how we can, decode the left-hand side into the much richer right-hand side.
Right. My understanding is related to the energy landscape,
Right.
because otherwise, you know, all confirmation will be equally good, right? There will be infinite number of confirmation.
Yeah,
Those
energy should
stable
be.
ones, right? I think they must have some kind of energy. Function.
I see. Yeah, so this framework, I think only the in the 2D graph, which takes as input only the graph structure and also the node attributes, including their, which can be divided into two input parts. There, like their features are sent as input. There's no kind of an overall like total energy that serves as the guidance here. So I think maybe in short, we agree that for this problem setting, which is relatively new to us, like for for this molecular graph generator, for a given 2D graph input, we are expected the model to get a set of reasonable confirmations that can preserve its local more of its local structure contained in these graphs. So that's probably the different setting compared to our traditional graph task, where each graph may correspond to a fixed set of labels. So let's move on to see what are the existing machine learning based approach to do such molecular generation. So the first work to achieve this is called CVGAE. So it is proposed in 2019. The key idea of it is that they send the 2D molecular graph as input to a GNN and to learn the item latent representations using graph neural networks. The whole framework adopted the VAE framework, and then the decoder is trying to directly predict item coordinates based on item representations. So one limitation for this model is that if you think about it as the generation property of a graph based on the confirmation based on the input G, likelihood of confirmation is not rotation or translation invariant. So that's something related to my previous quarter's presentation about equivariance. So I have previously shown some examples saying that there are many cases people care about equivariance. So for example, one type of equivariance is about translation equivariance. So we are all familiar with, for example, CNN. We see a neural network is equivalent to transformation if we transfer the input would result in the same transformation in the output. So CNN actually utilizes localized filter, and for an image, when we're trying to segment it to see whether each pixel contained a particular object, if we shift the like the input image by along a vector by some direction, then the output labels for these pixels will also change accordingly. So some other types of equivariance including, for example, rotations. So here saying that rotating two objects, if we want to do the object identity verification, it will not change the ground truth that, for example, on the right-hand side, these two objects, they are still the same cups. So more formally, like this equivariance we have previously introduced can be summarized as a following formula. So let us see a function T, a mapping TG be a set of transformations on the input X. We see a function phi is equivalent to this G if there exists an equivalent transformation on its output space such that when we firstly transfer the input using TG and then use the function to get the output is equal to we first apply the function to the original input and then transform the output using its equivalent transformation, for example, the same rotation or translation. So an example would be the aforementioned CNN. So see we have an input image, and on the left-hand side, I show that I first translate the input image first, and then run a CNN and get the output. And ideally, on the right-hand side, when I first run a CNN first, and I directly rotate the output, which is equivalent to this SG, I will get the same output for these two. Then we can call that this model is equivalent, like a base equivalence. So why we care about that in some short sentence that is that this equivalence can make our neural network more robust. And of course, one thing we can do is that we just provide sufficient training examples to let the model automatically learn from data that even if we translate or rotate an input, we'll still get similar transformation or rotation on the output to make the model know such principle from data. However, that will end the learning burden of the model. So a good thing is that recently people have started to use some mathematical tools to theoretically guarantee that our model is able to be awareness of that. So that during the learning process, since the model has already been be guaranteed to obey such equivalence, they can focus on learning the things that matters the most. So the following two figures shows kind of the comparison of non-equivalent models and equivalent models. So the dashed line actually is a ground truth one. And we can see for non-equivalent models, essentially because its prediction is based on the learning from massive data without directly encoding such mathematical guarantee for equivalence. There are some errors when we rotate the input and the predicted output would not 100% rotate the same thing as the input. But for equivalent models, we can see when we have special design to the neural network architecture, then the model itself can very precisely predict the corresponding action when we rotate the input one. So that's just some slides that are adopted from my previous discussion. So another thing that I want to mention here is that there's a difference between equivalence and invariance. So for invariance, what we call is that no matter what transformation we did on the input data X, our output would remain the same. An example would be we want to do the image classification where we want to output whether the image contains a cat or not. So on the left-hand side, the cat is on the right side, a right down corner, and on the second graph, we shifted by a vector direction, and still we want the model to predict it as 1. And for equivalence, giving the same example, it's more like another case that the task is trying to predict like the segmentation that whether each of the segment would contain the object cat. So when we shift the input image a little bit, the output will also follow the same operation. So that's basically the differences between equivalence and invariance, which we will look into these two terms when we talk about the model. Yeah, so that's the first work that's trying to do the molecular confirmation, where they adopt a VAE framework. The encoder learns the latent representations of nodes and edges, and the decoder directly trying to output the coordinates for all of these particles, so that it suffers from this like equivariance problem here. And later on, there are another branch of methods, which we can summarize it as two-stage generation method. So to give an example, there's a model called GraphDG, where they do the two-stage generation as follows. They firstly generate pairwise atom distances, and then they use some post-processing process to, based on this set of pairwise distances, to do the confirmation generation, which is that transform the pairwise distances to a possible solution of each item's coordinates. And yeah, please go ahead.
But in the little example here, it's not a pairwise, right? So some pairs do not have edge.
Yes. So so for predicting the pairwise distances, is that they predict the edges for the edge type, which is not that special type that I mentioned before, which is non-edge.
I can see that other than their bound there, right? There's some additional edges joined there, but for example, from like a V2 and a V3, there's no edge between them.
Yes. Yeah, for this work, I think they haven't introduced the long edge type, but for later on works, when they're trying to send into the whole graph to learn the whole node and edge representations, they introduce such long edge type. So for that part, I think this trick has also been utilized in some other works that we are familiar with. For example, like a neural relation inference, an RI paper by Thomas Keefe, where they're trying to get the infer the graph edges among pairs of nodes. So when they do the edge like generation or the latent graph structure prediction, they still have an edge types which is trying to see whether to see there's no edge at all between two items. So back to this case, for later on works that introduce such long edge type, when they're trying to generate the distance, if they firstly have seen that such edge type is a long type, then they will not generate the pairwise distances between these two items. And the reason they introduce such pairwise, that's long edge type, is that they still want to like account for the potential influence from a node that is not directly connected to another. So in the message passing procedure. Does that answer your question?
I'm still confused here. I'm reading like what's on your slides. You said first generate distance between items, which are in the translation equivalent.
Yes.
Let's assume that you have a rigid structure, right? You just have one confirmation. You don't have a two or more confirmation for the same chemicals, right? Because otherwise you don't have a fixed distance between some atoms. How do they generate the distance?
Yeah, I think the general idea for this two-stage generation is that the reason they want to pick this intermediate variable, say that pairwise distances, is because these pairwise distances is able to be invariant under rotation and translation regarding to the input, because distance is just a subtraction of two items coordinates, right? So it's naturally invariant under rotation and translation. So essentially, when they do the generation for this distance, as I said, they trying to send into the 2D graph into, for example, in a graph neural network, and then based on the inert representations to generate the pairwise distance based on the inert representation. And there are very complex procedures. For example, they adopt like bi-level programming later on, which they're trying to jointly do the distance prediction and from the distance to confirmation generation. Because one drawback for this two-stage generation essentially lies in that when they have errors accumulated at the distance, which is the intermediate variables they want, they will also accumulate the errors when they do the real confirmation, which is the coordinates generation. So they have trying to come up with some ideas like bi-level programming to alternatively training these two components.
Okay.
Yeah, but one good thing for this two-stage generation is that they all select to first predict this distance, because this will originally overcome the drawbacks that we mentioned in the first paper about the length of such equivariance property. So this two-stage generation approach in general, including this one, which is the newest one that is developing using normalization flow-based method to achieve this, they all share the good benefits that they can naturally guarantee the equivariance property by predicting the distance first. However, their drawback is that they can cause accumulated error for coordinate reconstruction, because they still serves as only a intermediate variable target for the model to predict. And also, if you think about the real case, when after they train the model and they actually need to use them, then there's some training testing inconsistent problem in that when you really use these two-stage models, you just firstly draw these distances, and then you like kind of finally what you got is just those coordinates instead of not only just these pairwise distances. So it's not directly a model that can serve for the purpose for testing. So that motivates.
Can I ask a question?
Sure.
Yeah, so maybe you already said this, but I missed it. So for the final construction of this 3D structure, do they need all pairwise distance, or they only need the distance between the distance of existing edges?
They only need distance between existing edges.
Then, yeah, then in this case, let's suppose I have a chain graph of say 5 atoms, like a 5 atoms connected by 4 edges, right? So I only need those 4 values to construct the 3D structure.
No, not only like the pairwise distance, but also based on the node representations, right?
But still, I feel you need more than that, right? Because there's a lot of a degree of freedom there, right? You just know those edge distance.
Yeah, but as I mentioned, because of this degree of freedom, so for those post-processing process where they generate the real confirmation from these predicted distances, they are not guaranteed to give you just one confirmation here.
Well, but if you don't have any constraint there, right, there will be infinite many number of confirmations. But in reality, they only have like, a small number of confirmations. because they have to reach a stable state. They can't really, move freely.
I think it maybe not find infinite number of confirmations, but the overall like goal this generation model want to achieve is that given these 2D graphs, they can generate one like reasonable confirmation so that it can be served as the generation purpose.
Okay, and you also mentioned for this so-called post-processing, they also needed node representation.
Actually, for this post-processing procedure, for those works that I posted here, they have different strategies to adopt. So traditionally, in this molecular generation domain, there are some traditional algorithm, mathematical algorithm that given a pairwise distances, they can give you a possible coordinates that can satisfy the distance constraints.
Right.
And but not all of like these two-stage generation paper that I mentioned here utilize such traditional post-processing stage. For example, one that I previously mentioned is the adopted bi-level programming procedure. And for that one, it is not just singly separating these two stages together, but alternative between these two procedures. Doing training. Yeah.
Okay, so I guess the first situation you described is closer to what I have in mind for a post-processing step. Like for example, I know the atom types, I know the edge distance. I can use some like mathematical tools.
Yeah,
or
like
maybe
some
domain
combinational
knowledge.
optimization approach to solve it.
Right, but for the second type you just described, if they still going to use the node representation, that seems like what we usually call like a decoder structure, right? Like maybe there are some neural network or something there. Is that correct?
Yes, and they are mostly based on the Knurling loss, the gradients of the Knurling loss of the inner loop and outer loop. And I think I can later on send that paper link to everyone, so we can also take a close look at it here. But the key idea I want to summarize in this these slides is basically trying to get the motivation that why these two-stage generation may not be directly ideally modeled for molecular graph generation, because they're like this separating these two stages, or even the take these intermediate variables into consideration and incorporating it in the loss function may not directly serve as the model purpose.
Okay.
Okay.
One quick question. So for the previous slides, right? Where you have the figure, you said, yeah, this part, so the distance is to be learned, right?
Yes.
And predicted from the neural network. So I'm trying to understand, like, if I know the two item type, right, of that edge, right, on the two end of that edge, two item type, is that bound, the distance of that bound, more or less fixed? Let's say if I have a carbon and another carbon, right?
Okay.
How much distance between, and I know there's a bound there in between them, how much distance between these two carbons, is that true? Is fixed?
You mean in the real world? Is
yeah, in the real world, yeah.
Yeah, I think to further explain like their training data, as I previously mentioned, they give abundant pairs of this 2D graph and the 3D coordinate pairs. So for this like 3D coordinates pairs because they just serve as the ground truth. So we know all of the coordinates of these particles. So of course we can compute their distance based on these given coordinates. But such coordinates may not be the only reasonable explanation for this 2D input graph, right?
Yeah, but you said that they only predict the distance on those edges where there's a bound, right? You don't predict all the pairwise distance, right?
Yes.
And then it's only on the bound that I feel like if there's a bound there, the distance is more or less fixed. Then why do we need to predict? We can do it much simpler.
You mean do not predict the distance?
Yeah, because if it's more or less fixed.
Oh, yeah, so the reason they want to predict the pairwise distance, take this intermediate variable, is mainly trying to solve the equivariance problem that I mentioned before. Because such pairwise distance, no matter you change the coordinates, whether translate or rotate, when you do this subtraction and compute the norm, essentially they will not change.
Oh, I see. You said that actually the VAE does predict all the pairwise distance, not just the distance on the bound.
Yeah.
Oh, okay. I saw that they only predict the distance on the bound. Then I feel like that's unnecessary because you more or less know the distance just from the pair of items on two end.
Okay, yeah, thanks for the clarification here.
Okay.
Yeah, so yeah, that's basically the summary for these two branches of work. So either direct generate the 3D coordinates separate from such equivariance problem, or we adopt those two-stage approaches. They basically can potentially have accumulated error and have truly testing consistent problem. So that motivates this paper to decide the algorithm that can preserve the rotation and translation equivariance of conformations, and in the meantime, directly conducts Merlin example in the coordinate space without any intermediate variables such as pairwise distance. So before we go to the model detail, let's firstly have an overall idea of the model development. So the model is called GeoDiffusion. So it's basically adopt the idea from a diffusion model to model the conformation process. The key idea is that they define a diffusion generated model that directly operates on the coordinates. So for the forward diffusion process, where we have the original conformation that we want, you can view the process as starting from the ground truth conformation, we adaptively and noise from a fixed posterior distribution, and until that this conformation has been destroyed. So this is basically the forward diffusion process. And for the backward generative process, where we trying to convert a chaotic conformation to its real conformation, then it's basically saying trying to firstly draw the chaotic conformation from a standard Gaussian distribution and progressively refine while the learnable induced Markov chain translation likelihood, which defines what would be the probability of conformation at timestamp t minus 1, given the input 2D molecular graph and the chaotic conformation at timestamp t. So this is also what we have learned in our course reading group. So in general, diffusion model have a fixed non-learnable forward diffusion process, and what our model trying to learn is the backward reverse diffusion process, trying to do the recover. So one thing here I said is that here this CT is sampled from standard Gaussian distribution. I will later on provide an analysis to see that why this is reasonable to assume this final CT can be sampled from this standard Gaussian distribution.
Yeah, I have
So-
a related question to this
Okay,
part.
please go
Because
ahead.
previously, when in our textbook reading group, we utilize image as example. So
Uh-huh.
then it's natural to represent image as a three-dimensional vector, and we can say, okay, it's sampled from a Gaussian distribution. So
Yeah.
here for the C, to my understanding, it has to be the latent representation of a graph, the 3D graph. Is that
Mhm.
right?
Yes.
So
So here you can view it as C. You can view it as a because what we want to get is a C0, which is a confirmation that we want. So what is the confirmation? The confirmation is every particle's coordinates. So what in real situation, what they did is just they concatenate all of the atoms coordinates together to form a long vector.
I see. So then my understanding was incorrect. So you're saying the C actually is a concatenation of all the coordinates of the atom
Yeah, and
instead of a latent representation of the entire 3D graph.
yeah, and you can also and you can also see that for all of this posterior distribution or the learnable Markov chain transition function, they are not just a condition on the previous CT, but also conditioned on the original input 2D graph G, where in this part they contain the learnable embeddings of those nodes and edges.
But here we just want to understand what's C in the concept model.
Sorry?
So it's the latent one, right? C, not latent? Latent representation, C.
You mean the C0?
All the C's.
All the C's, they should be in the same space, and we try to understand the semantic meaning of those C's. Are they coordinates?
Oh, they are like
or latent?
they
I
are
thought they're latent. No?
they are yeah, so the probability defined over this P and Q, they are defined over latent representation, but here this C, it directly refers to the nodes coordinates and their features. Yeah.
So all the C's are actual node coordinate.
Yes.
Then that relates to another question, how we decide the order. Because if you want to concatenate the coordinates, then for different node order, right, you're going to have a different vector here.
I think the order, because like all the transition function and the posterior distribution is also considered on this G, and I will later on show that these functions, they actually satisfied this like equivariance, including this permutation equivariance. So essentially,
Yeah, saying order does not matter. Just
yes,
a random order. It should be
because
fine.
if think about the generation process, we really need to utilize this model, right? So essentially, you send into the model a 2D molecular graph structure G, and then as I put it here, if you assume we have to do all the proof, then this CT, which is a final chaotic state, has been drawn from a standard Gaussian distribution. Then you can already utilize this model to get the real C0. So it's not basically like matters about the orders of the nodes, because during like the design, one of the key motivation for this paper is that they want to incorporate such equivariance property directly through the diffusion process by operating on the coordinates directly.
Then, okay, so if that is the case, then how we can interpret this C0 in the graph structure? If it's like image case, then random noise, just you can visualize that, right? The white noise. But then if the C0, the coordinates are sampled from, let's say, 3D Gaussian distribution, what does that mean when we try to translate that into this discrete structure?
It's not it's not about the let me put it in this way. So here again, back to our problem definition, we have this input 2D graph. So we already know which nodes are which nodes are connected, which nodes are not. But the thing that we are missing is that we do not know their 3D coordinates in the coordinate space. So essentially, here when we end the noise, it's essentially we're trying to firstly assume all of these nodes, their coordinates follows the standard Gaussian distribution, but we want to originally denoise these coordinates back to its real one.
I mean, we don't need to worry about the graph structure part, just we assign the coordinates randomly.
It's not without graph structure, because all the denoising procedure is based on the given 2D structure, right?
Yeah, I'm just talking about a C0 part. So we don't need to worry about decode that into a graph structure, because it's already given. What we need to know is just their coordinates.
Yes.
Okay.
I think Znil has sent something on the chat box.
Yeah, Fred also has got some comments.
Yeah, let me take a look. I think Znil says that the graph is given as condition with a fixed order, and C represents a full set of positions matrix. Yes, so again, like this C only contains like the coordinates of each of these items, and we get like their structure. We try to generate their coordinates based on their given structure contained in the G.
I see. I think I earlier had the impression that they're going to generate the graph, but actually it's not. They just try to generate the coordinate.
Yeah, because like the problem input here, maybe I haven't emphasized it too much. So they have this molecular graph G as an input in order to generate its confirmation.
Okay, sounds good.
Okay, yeah, thanks for those points. Let me go back here. So essentially, after we briefly look at this forward diffusion process and the backward generative process, the key challenge is how to efficiently optimize the reverse diffusion process probability, and in the meanwhile impose the SE3 equivalence. Here, previously we have a brief recap of the SEN equivalence, where the N is the number of coordinates of these particles. So now we consider in the 3D space, so it's called SE3 equivalence. So, so for the forward like diffusion process, as mentioned before, it's a fixed, not learnable process based on a list of fixed variance scheduling. So essentially, it's similar as what Znil has introduced in Thursday's lecture. So for the forward generation process for confirmation from time 1 to time t, its posterior distribution is modeled as a multiplication for each of these Markov chain. And for each of these Markov chain is based on the standard formula where we have these following a Gaussian distribution where beta t is basically defined as like how much you want to like if we define alpha t as 1 minus beta t, it basically says how much you want to preserve in the previous diffusion process. So here what I want to show is that as I mentioned in the overall framework, for the backward generative process, we will sample the CT from the standard Gaussian distribution. Here I want to show that with why is that is because with sufficient large T and following this formula, this forward process will eventually convert this CT to the white isotrophic Gaussian, and thus it is natural to set this PCT when we do the reverse diffusion process as a standard Gaussian distribution. So actually the proof is quite simple. So again, let's try to see if we define this alpha t as 1 minus beta t. And here we have this formula where each CT actually can be rewrite as square alpha t CT minus 1 plus square beta t epsilon t, where epsilon t is a standard Gaussian distribution. This is because when we multiply two Gaussian when we add two Gaussian distribution together, see Gaussian distribution mu1 theta 1 square I plus mu2 theta 2 square I, then it will give us this addition of their location and the addition of their variance. So we can just rewrite firstly according to this fixed posterior distribution that CT can be represented. If we view each CT minus 1 as a random variable associated with probability, we can write them in this way. And we can further decompose this CT minus 1 using CT minus 2 by doing like the further on like expansion. So each of these delta t minus 1 delta t is just the standard Gaussian distribution. So we expand until we reached C0. So what this will give us is that we can actually see that this will give us the multiplication of alpha t minus 1 until alpha 1. So essentially of C0, this would be when we further expand this t minus 1 into smaller loops. And then we, for the delta t term, what we have is like alpha t minus 1 until alpha 2 beta 1 epsilon 1 plus beta t epsilon t. So now let's look at this addition for this standard normal distribution. So again, because all of their location parameter is 0, so of course there will be a 0 mean Gaussian distribution. And for their variance, we just take the addition of their squares. So this will give us alpha t minus 1, alpha 2 beta 1 plus alpha t minus 1 beta 2 until alpha t beta t minus 1 plus beta t. So in this sense, finally we can, because each of these beta I, you can further like rewrite it as 1 minus alpha 1. Here this is 1 minus alpha 2, etc. So essentially, for example, for the first term, like alpha t minus 1, alpha 2 multiplied by alpha 1, this when we expand this, this will be 1 minus alpha t minus 1 until alpha 1. And for this term, it will be alpha t minus 1 until alpha 3 minus alpha t minus 1 multiplied by alpha 2. So so essentially under this case, for each of these terms, they were going to like the previous one would like cover the like the first first term will be the negative term in the next term. So essentially, after all of this submission, we finally, what we have is only this 1 minus alpha t minus 1 until alpha 1. So essentially, what this gives us is that the final representations for this C T actually can be represented as the so in this sense, so essentially we can observe that for its new location, it can be defined as a multiplication for this alpha 1, alpha 2 until alpha t. So let's imagine when this t approaches infinitely number. So essentially, because we define this alpha t as 1 minus beta t, which is larger than 1. So essentially, for this value, it will convergence to 0, and for this one value, it will convergence to 1. So what this procedure shows is that through the forward diffusion process that we define here, from C0 to CT, eventually this CT will convergence will be chaotic following a like standard Gaussian distribution. So that's why when we're trying to learn the reverse diffusion process, or when we really use the model to do the confirmation generation process, we will sample this last like chaotic state CT from the standard Gaussian distribution. So that's one thing we have when we follow the traditional to define the forward process as a non-learnable and fixed procedure here. And so, yeah, so that's basically like an explanation for the assumption why we later on do the reverse process. We will sample from standard Gaussian. But the key challenge design in this paper lies in how they trying to make this learnable reverse diffusion process equivalent. So as mentioned, the in the overall picture, the reverse diffusion problem is trying to recover the conformation C0 from the white noise CT. So essentially, we can rewrite the reverse Markov. We usually rewrite the reverse Markov chain probability as the location is conditioned on both the graph conformation and its previous conformation CT. And so this mu theta is a learnable module, and this sigma t squared is basically can be any user-defined variance. So the key challenge lies in how to make this procedure follows the equivariance constraints. So based on the Markov assumption, when we decomposed this reverse diffusion process as a multiplication for each of these conditional probability, then when we do the marginalization, we can directly get the p theta C0 condition on G as the integral of p CT, which is a prior distribution of the late of the last chaotic conformation state multiplied by the the remaining Markov chain reverse generation procedure when we condition on the CT and to generate CT plus -1, CT -2 until C0. So in order to make like this procedure to satisfy these equivariance constraints, what we have to do is to ensure two things. One is that they need to guarantee this PCT should be an SE3 invariant density function, meaning that for any rotation translation operated on this input CT, like the coordinates, they will not change the density distribution of it. And the second thing is that because this chain, like Markov chain assumption, this C0 till T minus 1 procedure can be further decomposed as multiplication of each of these P x T minus 1 condition on xt. So they also showed that if they can condition by revise it as a multiplication of this one. So they also show that in order, besides that, the initial density function of CT must be invariant. The Markov transition function should also be equivalent in order to satisfy this. Why now it should be only equivalent, not invariant, is because this is a conditional probability. So even if the output of the xt minus 1 should, if we consider that it is only equivalent, then the output of this tgxt minus 1 should also be like the original output transformed by some like operations C SG. But since it's a conditional probability and the xt's original output would be also transformed by the same like operation. So essentially, the second requirement would only require the Markov transition function to be equivalent instead of invariant. So that's basically the analysis to the marginalized formula. So what they need to do next is trying to satisfy these two constraints, where firstly, the invariant, they need to find an invariant initial density for PCT, and secondly, they need to find an equivalent Markov kernels defined based on CT minus 1 given G and CT. So to solve the first challenge, what they did is that they set this PCT using a COM free Gaussian. Here, COM is denotes the center of mass. So essentially, the key insight is that Gaussian is rotationally invariant, and by moving the COM to 0, it can be also translational invariant to ensure like we satisfy that this PCT is SE3 invariant. So in order to prove this, we can firstly show that firstly for each not COM free system, maybe I can firstly introduce like the COM system. You can imagine for each of these particle, it has its coordinates. So and each of its coordinates have its corresponding density function. So the summation of its density function multiplied by its real value, like its coordinates should be sum up to 0. That would be a COM free Gaussian. So we can always transform. So why we change this, why we choose this COM system to guarantee such equivalence is that for each system X that is not COM free, we can always transform it to a COM free system by multiplying it with a Q defined as here. So the Q, we can observe that it is symmetric projection matrix, as we can easily compute Q multiplied by Q is Q itself, and its transpose is also itself. So in this way, actually, because X itself follows like we see that it is sampled from a Gaussian distribution, then we see when it multiplied with a Q, we can easily get that the new random variable y, which we defined, for example, as qx, its new distribution is also a Gaussian, but with a multiplication for its mu and like matrix multiplication for its standard variance. But since, let's see, we hear this x hat is a COM free system, meaning that this mu x itself is 0. So in that sense, this new transformed one, it also has zero mean Gaussian distribution with only changes to its variance by doing some matrix multiplication. So that means say that for each CT, for example, here, when we sample it from a standard Gaussian distribution, but the sampled CT, it is not a COM-free system. We can always transform it by subtracting the average of each coordinates for each of the particles to guarantee that, okay, this system can achieve this translation and rotation environment, because rotation environment is naturally guaranteed by the Gaussian distribution. For the translation environment is that for each of these non-COM free system, we can transform it by this symmetric projection matrix. And once we set this COM system to 0, then no matter how we translate it, then it will still have a 0 mean. So that's the key idea. That's the adopt from ICMO 2020 paper to achieve this invariant initial density problem. So this is the first step to solve this question. So for the second step, we need a solution for developing an equivariant Markov kernel. So here, again, remember it's equivariant, not anymore invariant. So what they have choose is similar to what I have introduced in previous quarter. They utilize the equivariant graph neural networks, because as I said here, for this Markov chain kernel, here this mu theta is defined via a learnable NN, where you can see this mu is computed conditioned on the CT and also the graph G. And following the recent progress of diffusion models, we consider the which is also introduced in the news lecture following the paper denoising probabilistic diffusion model. People usually will reparameterize the means function using the following formula. So here, so back to here, what we have to achieve is just to ensure this epsilon theta, this arrow function, to be satisfied this equivariant, because we have already shown that how we make this CT by utilize this COM free system to be like a invariant like representation. So the key, so the implementation that they choose for this sigma theta is based on the equivariant graph neural network, where the key difference for this neural network compared to other GNN architecture is that they not only updates, they not only associate, the message passing part is not only associated with node features, latent node features, but also associated with the pairwise distance functions between their coordinates. And x, their coordinates x is updated as a combination of weighted radical directions defined here. Here, each of these Ci, Cj is a real coordinates, which is a 1/3 vector. And here, this xi L plus 1 is a latent representation of their coordinates. So I have done the proof in previous quarter how this network have preserved the equivariance property. So probably everyone can refer back to that, because that's not the main novelty for this paper. But for a brief recap summary of how we understand this is that by looking at the first equation, we can see that each node's feature, they are invariant with regard to rotation or translation. And here the distance between two particles, they are still translation and rotation invariant. So that means the first formula, the message part, Mij, is itself is invariant. And then we can see this x is updated with the weight computed by the relative differences, by the relative coordinates differences multiplied by the weight computed from the message. Since the message itself is invariant, so essentially this will give us like this xil plus 1 itself. This latent representation for coordinates will also be like translation invariant and rotation equivariant. So for more detailed like proof, you can find my previous quarters slides for the detailed proof. So that's basically the key contribution that they made for defining the reverse diffusion process. To sum up, they firstly do some analytics showing that the in order to achieve these equivalence constraints defined in the reverse diffusion process, they need to satisfy two constraints. One is that the initial density function needs to be SE3 invariant, and secondly, the Markov kernels defined in the reverse diffusion process need to be SE3 equivariant. And they utilize the COM-free system to achieve the first goal and utilize the equivariant GAN to achieve the second goal. And finally, towards the training, it still follows the standard diffusion model by optimizing the variational lower bound, where for each of these Q CT minus 1 condition on CT, because this is the like the fixed forward process, so it's have the analytic form, which is also showed in Znil's lecture. So basically, it follows this closed analytic form. So essentially, for each of these KL divergence term, it's just the KL divergence measured from these two Gaussians. And for such like object function, it can be further simplified by utilizing the like the parameterization, where we set this mu theta CT as in this equation. So this is also showed in the denoise probabilistic diffusion model introduced in last Thursday, so that it can further simplify our objective function to do the training. So we can understand that this intuition behind the objective is to independently sample chaotic conformations of different time steps and use this arrow sigma theta to approximate the noise vector. So when we train the model and when we want to apply the model to do the real confirmation generation, what the procedure goes is like this. So we input firstly have a molecular 2D graph, and we also have NERD reverse model. And we firstly will sample this its chaotic final diffused conformation from a standard Gaussian distribution. And for each reverse diffusion step T, from T minus 1 until 1, we will shift this CT to a zero center of mass system by subtracting each of the coordinates by their average. And then we will compute this mu theta based on the formula we defined here, where this epsilon theta is defined using a equivariant graph neural network to guarantee such kernel is equivariant. And after that, we will sample this the previous chaotic, like the recovered chaotic step CS minus 1 from the Gaussian distribution here, which is basically defined in the forward, like similar in the forward process, whereas the mu is computed while the like equivariant graph neural network based on the previous CS. So that's basically when after train the model, how we use this model to do the confirmation generation. So again, as you can see through this procedure, the main design is that we do the shifting to make this each of these CS to be 0 COM, and secondly, compute the mu of each CT following the equivalent GM design. So for their experiments, they conduct, they use the data set which contains over 33 million molecular conformations by MIT material group, including both small moleculars and medium-sized drug-like moleculars. And the baselines they selected are majorly the ones I have previously talked about in the related work, where the first one is a VAE-based framework. They directly generate the coordinates. And the remaining three are trying to alleviate the intermediate variable, which is the pairwise distance, and serve as two-stage approaches to address this problem. And finally, this is a traditional machine learning-based method, which have very slow speed to generate those conformations. And for the evaluation, they adopt the following two standard metrics. One is called the coverage. Like, as I said, for each of the input to the graph, they have a set of conformations, which we call the reference set. So the coverage is defined as a fraction of conformations in the reference set that are matched by at least one conformation in the generated set. And the second score is called matching, which measures the average distance of the reference conformations with their nearest neighbors in the generated set. So, essentially, they evaluate over both of these two metrics. And here are the results we have shown here. So in general, the proposed GeoDiff method is able to achieve the state-of-the-art performance on all of these four metrics. And by looking at the comparison, this is the comparison for those machine learning-based approach. And by compare it with this traditional material science-based approach, it can still achieve better results, even with faster speed compared to the traditional non-machine learning-based approach. And finally, they also studied that because they define the diffusion process based on the timestamp t. So even if they shorten their timestamp t, which is the total timestamp they do in the diffusion process, they are still able to outperform most existing ML models in the previous slides. And here are the generation visualization for their methods. So we can see that for each of these rows, we have an input graph, and the right-hand side is the set of valid or reasonable combinations that it can generate based on the input graph. So, so from this illustration, back to our previous discussion about the problem definition, I just feel that for each of these confirmation, they can be both the change of some of their local distances, but it will not exist the second confirmation, for example, that has the first confirmation shift or rotate by an angle, because in their original design, they have already guaranteed that this will not happen no matter you change the input, and similarly the output will not contain such redundant confirmations where they only globally do a shifting or a rotation. And the second task they conduct is called property prediction, where they try to predict the ensemble property of molecular graphs, which is kind of viewed as the global properties of the whole graph structure. And the way they achieve this is by aggregating the property over a set of generated confirmations. So, and they directly utilize the mean absolute error to validate the to measure the properties that they predicted. So from the results table, it still shows that the proposed method achieves superior or comparable results over all ML-based and classic-based methods. And yeah, so that's basically about all the experiment results in this paper. And they also mentioned several future directions they would like to explore. So they would like to extend the general framework to some more challenging structures, such as proteins. So probably contains multiple compounds from where the input graph is not a single molecular, but can be a more complex structure comprised of several several such local structures together. So it can be viewed as a more gigantic graph, and to see whether we can directly generate the conformation given such gigantic graph. And the second is that they want to tackle more realistic setting like predicting protein binding positions. So essentially they were trying to see whether they have the ability, besides predicting the conformation which is their coordinates, and by aggregating their conformation to predict properties, whether there are some other tasks they can easily achieve. And they also want to explore whether they can further improve or accelerate the current method with with some most state-of-art diffusion models like non-Markovian sampling to make the performance even better. And more broadly, view this method as the first step to marry geometric learning with advanced probabilistic model, which is a diffusion model. And in the future, they are interested in further exploring to see whether they can combine these two areas better. So I also found a more related work recently, which is published in this year's ICML from Max Billings group. This is called equivariant diffusion for molecular generation in 3D. I look at the paper after I read the GeoDiff paper. I found that basically they did more improvement on the molecular generation method development, in that they have the ability to handle discrete atom features, and they furthermore derive the equations required for log likelihood computation to further save the training time. So I can see there are many recent works are trying to dive deeper in this direction, especially when they do the generation procedure. They would like to provide such equivariance or other geometric properties mathematically to make the model more robust and powerful. So I personally think that there are still a lot of space to further explore. Okay, so that's basically, we are running a little bit out of time. So any other questions?
Yes,
Thank you.
I have a question, a quick question.
Oh, sure, go ahead.
Yeah, so yes, thank you for your presentation. So I think in both of the papers, in this Max Williams paper and the GeoDiff paper, they didn't really change the graph structure. They only care about the coordinates, right?
Yes.
Do you think that changing graph structure, like learning the, do some structure learning along the way, would that help for this task or no?
I think it depends on the problem you want to solve. If you think that, okay, there's some noise in your 2D molecular graph data that probably if you directly condition on such graph structure, it will not give you some accurate 3D confirmation. We can also end such structure augmentation as in your last Tuesday's presentation into this generation process. But I think for now, in their general setting, they just assume that they take this input graph, they think their data are clean, and they want to see, based on this given input correct 2D molecular graph, whether they can directly generate their 3D coordinates.
Okay, thank you.
Thank you.
Yeah, also I fear if we are able to, for example, model the diffusion in the latent space, right? The potential we can completely generate the graph structure. So we don't have to have the input structure.
Yeah, I
Yeah,
agree with, go ahead.
sorry, please go ahead.
I agree with you, Joe. So it's already I saw that they work in the latent space, but you said that they actually just use the coordinate space. Another question I have is I don't see a place that actually they consider any of the energy function, right?
Yes, there's no consideration for the energy function.
Right. So I was wondering whether I mean, if they incorporate the energy function, because if you look at what the chemist is doing, right, they actually traditional way of their doing that is really try to, I mean, work on the energy function and doing some differential equation and things like that. So I wonder if they're incorporating that with the graph that might help.
Yeah, I think maybe incorporating the energy for the whole system in the consideration as like the PhD student from Professor Marcia's group, what she is doing, I think she already showed that it will give more like constraints to avoid more freedom. So I think it's worth trying here. I think, Sunil, do you want to have some comments directly by speaking out?
Yeah, I just added 2 comments in the chat. The first is, like answering Ijo's comments, currently the SOTA diffusion model right now is exactly doing the latent diffusion. So, but their motivation is mostly from like inference perspective, because the previous GGPM and GGIM like diffusion sampling in like the like a latent variable space is very slow, especially if we consider like, for example, image pixel as like the like sampling space. It takes much longer like steps to generate high quality images. And then right now, like many of the good demos I showed in like last Thursday is based on a very recent CPR work called latent diffusion. And I think like later on, Patricia will introduce this work in detail. The second comment is that there is a very recent several preprints about doing the graph generation via diffusion. But I think they are at very, very early stage and just didn't do much of the careful design, and the result is not very comprehensive. And there's like still a lot of space to explore. Yeah.
Okay. Yeah, thank you, Sunil, for the comments and the pointers.
I have a question regarding their future direction about modeling the protein ligand binding, right? So, because they do they need to model all the pairwise distance, right? I wonder the scalability of their model, because for the chemicals, it's a very small, right? So,
yes.
But if you scale up to proteins, especially large proteins, if you also want to model at the atom level, that would be millions and tens of millions, could be up to that big, the number of nodes.
Yeah, I think for, as they mentioned, currently they only handle relatively simple structure like molecular instead of like proteins. So essentially, when the graph size becomes much larger, I think there should be more careful design towards the scalability issue.
Yeah, because in their future work, the second line, they mentioned protein ligand binding.
Yeah, yes.
Yeah, so that makes me wonder, like, how do they plan to do that?
Yeah, maybe I'm not super familiar with this area because when I look at the work done by this author and his collaborator, I think they all just focus on the like the not the protein level, but just on the molecular level.
Yeah. Okay.
Yeah, I think that's definitely maybe a good direction if they really want to move it into like real applications.
By the way, for protein, I'm not the expert of that direction, but when I collected the paper list, I just find out one recent paper from Tommy Giacalo's MIT's group that doing a task called the bindings, particularly the binding structure, which is linking a small molecule to a protein. Yeah, again, I'm not the expert, but I'm not sure whether this is exactly the one of the direction of doing like these tasks. I also send that paper in this chat.
It is a diff doc, that one?
Yeah.
Okay.
I'm not sure whether is this the task that Professor Wang is thinking about, or one of the directions.
One of the, I'll just look at one of the future direction there.
Yeah, I believe there's a lot of things that could be done by combining these two words.
Yeah. I believe so, because Roshni, Yanqiao, and Jay and myself went to like a meeting last week about AI in chemistry. So there's a lot of interesting problems.